Hello friends, welcome to my channel. Keep exploring. In today's video, we are going to solve a question from the exercise 1.1 of real numbers class 10. So let's start. So the question says, so that any positive integer is of the form 6q plus 1 or 6q plus 3 or 6q plus 5, where q is some integer. So let's understand the question first. So here we have to find a positive odd integer. So we have to say that any odd integer is of the form 6q plus 1 or 6q plus 3 or 6q plus, where q is some integer. So here we say that whenever we are taking any positive odd integer, whatever even or odd, the q what is there, it is always positive. We'll consider it as a positive, although it is not mentioned here, but we'll consider it as positive, because positive, when we are dividing by another positive, we'll always get a positive integer. So here the next thing what you have to see is this one, the forms. So as you can see here, the forms of this integer are 6q plus 1, 6q plus 3 or 6q plus 5. So here the most important thing is 6. That means an integer is there, that one we have divided by 6, then only we will get this form. So this one you have discussed in our earlier videos, that is how a integer is formed. You can get the link of that video in the description box so that you can understand it better. So here we are considering, let there is a positive integer a, let a be a positive integer divided by, we will take it as divided by 6. Because only by seeing the form only it is easy to understand that an integer is being divided by 6. Now here what you have to see, now a is being divided by 6, so by using Euclid's division lemma, so by using Euclid's division lemma, what we get, a is equals to 6q plus r. Same thing, when a is divided by 6, we get a equals to 6q plus r, where r is less than 6 or greater than equals to 0. So this is the lemma. You can get the concept of Euclid's division lemma in the description box. So here a equals to 6q plus r, where r is less than 6 but greater than equals to 0. So r has the values 0, 1, 2, 3, 4 and 5. These are the 5 options we are having for the remainder. So r can be 0, it can be 1 up to 5. So see here, when we put r equals to 0, what will happen? A will become 6q plus 0, it is 6q1. So similarly, when r equals to 1, what a will become? 6q plus 1. When r equals to 2, a is equals to 6q plus 2. When r equals to 3, a equals to 6q plus 3. Similarly, with 4, a equals to 6q plus 4, and the last one, when r equals to 5, a equals to 6q plus 5. So this one we have seen already in our earlier videos. So whenever we are getting a remainder, according to the remainder, we can change the forms here. So a becomes 6q, then 6q plus 1. Now let's see here. Now we'll come back to our proof. So what you have to prove? 3 of them, that is 6q plus 1, 6q plus 3. So this one, 6q plus 1, 6q plus 3 and 6q plus 5 are odd integers. You have to prove it. So let's see. So let's take the forms. First is 6q. So a equals to 6q. Another one we have 6q plus 1. Then we have 6q plus 2. Then we have 6q plus 3, 6q plus 4 and 6q plus 5. So these are the options we are having. So the remainder will be 0 to 5. So let's say each of them. First thing, we have to prove them as odd integers. So odd integers means it is not divisible by 2. That means we cannot write in the form of 2 into something, or it will be not divisible by 2. Okay, let's see here. So what we do? First involve. The first form you can see is 6q. Now 6q can be written as 2 multiplied by 3q. So as I said earlier, if I can write this as a form of 2 into something, 2 into something, it is always an even integer. Okay. Next, 6q plus 1. So 6q plus 1, from 6q I can take 6q can be written as 2 into 3q, but 1 I cannot write. So here we say that this part is divisible by 2, but this is not divisible by 2. Hence this is an odd integer. We'll take it as an odd integer because you can see here we are getting a remainder one. Now 6q plus 2. First let's consider 6q, then we'll consider 2. Now when we take out common, so what we get from 6q, I will get 3q, from 2 I will get 1. So it is clear that 2 into something we are getting. So here 2 into 3q plus 1. So this shows that 2 into something, that means it is always even. Next 6q plus 3. So 6q can be factorized as 2 into 3q. But 3 I cannot divide it by 2. We cannot take 2 as common. So remainder is as it is 3. So this is divisible, but this one is not divisible. Hence this is an odd integer. So we know that any integer can be either even or odd. Any positive integer can be either even or odd. There are the two options. If it is not even, that is odd. Next 6q plus 4. It is divisible by 2. 6q is divisible by 2. 4 is also divisible by 2. So it is an even integer. And this form 6q plus 5. Okay, 6q is divisible by 2, but 5 is not divisible by 2. As you can see here, from 5 I cannot take out 2 common. So this remains odd. So here what we find, 6q plus 1, 6q plus 3 and 6q plus 5 are the forms of an odd positive integer. So here we can say any positive odd integer can be written of the form 6q plus 1 or 6q plus 3 or 6q plus 5. Now a simple thing I want to say here. So when you say 6q plus 1, 6q plus 3, now 6q plus 5, how we can say these are odd? Already we have seen the proof, but for example, you take q as 0. Okay, for q as 0, what it will become? So what will be a now? 6q plus 1. So 6q plus 1 means 6 into 0 plus 1, 6 zeros are 0, 0 plus 1, 1. Now a will be 6q plus 3. So 6 zeros are 0 plus 3 will get 3. Next a equals to 6q plus 5. 6 zeros are 0 plus 5 will get again 5. Now here, so you can see all are odd integers. Now for the same thing, suppose I take now q as 1 for example. So what will be a here? 6q plus 1. So 6 ones are 6 plus 1 we get 7. What will be 6q plus 2 then? Sorry, plus 3. 6 ones are 6 plus 3 we get 9. Then we have 6q plus 5. 6 ones are 6 plus 5 we get 11. So you can see here we are getting always an odd integer. So any positive odd integer can be written of the form 6q plus 1, 6q plus 3 or 6q plus 5. Hence that's the solution of this problem. Hope you have liked this video. To get more such videos, please like, share and subscribe my channel. Keep exploring. Thank you.